Hello and welcome to this FMSP online revision recording for the MEI specification Module D1 Decision Mathematics, and the topic is networks. Under that heading in the specification we find four sections. The first is just reminding us that a network is a graph of the type we've met before with weighted edges. In other words, we now have numbers on the arcs representing perhaps distances or journey times or whatever the question demands. Secondly, that we use these to model situations. Very often they're geographical in the sense that they're to do with distances between towns, but they can represent other kinds of problems, including the ones listed here. Now, very specifically, we need to know about the minimum connector problem and the shortest path problem, which means we're talking about Kruskal's and Prim's algorithms, Kruskal's on a graph, and Prim's on a graph or in a table. And then for shortest path, Dijkstra's algorithm, and we'll see examples of Prim's, Kruskal's and Dijkstra's in this presentation. So straight on to our first examination question then. And this matrix gives us the distance in miles between towns where a direct route exists. So for example, there is no route from A to C, nor therefore from C to A. And you wouldn't expect a route from A to A, from a town to itself, or at least if there was one you probably wouldn't take it, you'd stay put. Another thing to notice, always worth just checking when you've got information about distances in a table, is to consider this line of symmetry halfway down the table, down the centre of the table rather. I noticed 22 and 22, 6 and 6, 26 and 26, and yes, we do have all the same distances below that dotted line as above, and that's because there are presumably no one-way routes where it's slightly longer one way than another way. And therefore we simply do need, when we draw the network in a moment, to add one edge for each of these values. 3 routes from A, 1 from B to F, 3 from C, and 1 from E to F. Let's just have an overview of the question then. Firstly, we're going to draw the network, and then use Dijkstra's algorithm to find the shortest route from A to F. Then, in the third part of the question, we're going to use Kruskal's algorithm to find a minimum connector. And I just want you to notice part 4 here, because rather than leave it to the end, I'm going to consider this at the end of part 2 and at the end of part 3. Because the question is, how much shorter would AD have to be if it were to be included in your shortest route from part 2 and your minimum connector from part 3? Okay, let's do the question then. They give us a framework of vertices to use for our network, and then reading carefully from the table we add the edges, only the ones we need, and put the lengths on them. So here's my solution to part 1 of the question, which by the way is worth 3 marks. So be careful to put only on the edges that you need, and one of those marks is for correctly labelling on all the lengths, and do make sure they're not ambiguous. I've carefully placed my numbers so that 12 couldn't be mistaken for the length of either of these arcs, for example. Okay, well, our first job then is to do Dijkstra's algorithm to find the shortest route from A to F, and of course we're using the box method, which I'm sure you know well. In the box method, the top left value is for the order of labelling, and as I'm starting at A, this will be box number 1. The top right is the distance from A to the vertex, so from A to A is 0, and at the bottom go the working values. There are none, of course, at the moment for this first vertex. The working values are very important because they give us evidence that the algorithm has been correctly applied, so make sure your working values are all legible and don't cross out superseded values, leave them visible for the marker to check. Okay, I'm at vertex A and I consider all the connections from A. It's a distance 0 so far, plus 22 gives me 22 to B. Then 0 plus 12 gives me a distance 12 to D. 0 plus 10 gives me a distance 10 to E, and that's all the connections from A. So step back and look at all the working values so far and choose the smallest, which is the 10 at E. So that becomes the permanent label, which means the permanent distance from A, and it's box number 2. Now imagine you're at E and do all the connections you can from there. So a length of 10 so far plus 26 gives me 36 at F. You don't do the one which is 10 plus 10 to A because I've permanently boxed A, and that 10 was the way I came anyway. So you needn't write in any working values to a vertex that's already been finally boxed up and finished. We do have another one to do. 10 plus 5 is 15. Now once again look at all the working values and pick the smallest, which is the 12. The 12 at D becomes the permanent label, and it's box number 3. So I'm at D. What can I do? Well, not that connection, but 12 plus 6 is 18 should be considered, but I won't write it in. Don't write in working values that are less good than the value that's already in there. So I've worked it out and checked it, but I don't need to write it down. So once again, step back and look at all the working values. 15 is the next best one. So 15 becomes the permanent label, and this is box number 4. Again, consider where I can go from C. Well, not to D, that's permanently labelled. Not to E, that's permanently labelled. But I can go across to F. 15 plus 11 is 26. That is a better value, so I'll write that in. That's all the connections from C. So now, once again, look at the remaining working values, 26 and 22. So that 22, which is the lowest of the remaining working values, becomes the final label at B, which is box number 5. Now, I'm at B. What connections do I need to consider? Nope, not that one. That's already permanently boxed. So I have 22 plus 13 is 35. But I don't write that in at F because 26 is lower than 35. So that's finished with the working values, and let's look at and see the best one so far. Well, there is only one left. It's the 26 at F. That becomes the final label, and it's box number 6, and I've finished labelling. Now I need to work back to find my root, and the root will be the only root on which the calculations are correct. So for example, 26 take 13 isn't 22, so it's not that one. 26 take 11 is 15. Yes, it is that one. 26 take 26 isn't 10, so I've just checked, but it is the only correct one. Okay, from here, 15 take 6 is 12. No. 15 take 5 is 10. Yes, so CE is required. And then 10 take 10 is 0. Yes, that's the last step of my root. So as you should always do, let's state the shortest root and its length. And the shortest route starting from A to F, and give it in that order, even though we found it in reverse order, is AECF. And the length of that, which can be found on vertex F, is 26. And look back and write the units. It's 26 miles. It's a small touch of finesse, but it's always nice to give the units on an answer at this stage. Now let's just consider how that's marked. There's one mark for, broadly speaking, following Dijkstra's algorithm. Sorry, I've been used to pronouncing it the other way for so long, so apologies if you hear me say it both ways in this presentation. One mark for that. Secondly, the working values. I can't emphasize this enough. The working values give the evidence that the algorithm's been correctly followed, so they will be checked. A third mark is for getting the orders correct. In other words, you've boxed the vertices and the top left numbers are all correct. And lastly, the actual distances from A to each vertex, that is the labels, are correct. So there's your 4 marks, plus 1 for stating the route and 1 for stating its length. Now then, I want to just reflect on part 4, even though ideally I'd leave it to the end of the question, but now that we have the picture in front of us for Dijkstra's algorithm, the question is, how much would you have to reduce AD by for it to have been part of the shortest path? Okay, well, the shortest route at the moment is A to E to C to F. The total of that is 26. If you were to include this 12, it would have to be the first step. So the first thing you'd have to do is go from A to C, and A to D. Let me correct that. And if you did use AD, you'd probably then use the 6 to get to C, and then go from C to F. So ADCF would be the route if AD was short enough. So how short does it need to be? Well, DC is 6, and CF is 11. That's 17, but we already know that the best route has length 26. If this is 17, I think AD would have to be 9 to equal that route. So I find myself thinking AD would have to be less than or equal to 9 to be considered as part of the minimum, as part of the shortest path. Well, in fact, if AD was equal to 9, that would be good enough, because it would be an alternative shortest path. But make sure you answer the question, because we need to know how much AD needs to be reduced to be part of the shortest path, and therefore I'm going to say it needs to be reduced by 3 to get down from 12 to 9. There is only 1 mark for giving the right answer, so although I've written down my reasoning, there is a mark for saying either AD equals 9 or AD is reduced by 3. Okay, let's now move on to the next part of the question, which is to use Kruskal's algorithm to find a minimum connector. Okay, Kruskal's algorithm concentrates on picking the best edge, in this case the shortest edge, and the next shortest edge, and the next shortest edge. They don't have to be connected as you choose them, they can be in any part of the network, but you must avoid making a cycle. And one more thing, when you have n vertices in a network, you're going to need n-1 edges for a minimum spanning tree or minimum connector. So we've got 6 vertices here, we're looking to choose 5 edges. Okay, well, let's have a look for the smallest, and I can see that 5 there, so EC, CE I'll write it is, as is my first choice. And then the 6, CD. And the next smallest is the 10, and round about now I've got to start checking that I don't make a cycle. Well, that one clearly doesn't. That's AE at 10. And notice I'm listing them downwards, so it's absolutely unambiguous the order in which I'm choosing these edges, because the order of choice is the evidence that you followed Kruskal's algorithm correctly. Okay, next one then, there's an 11, that's CF. Yes, I'm just checking it doesn't make a cycle with anything else. So I can have CF for 11. And the next is the 12, AD. But hang on a minute, A is already in the set, and D is in the set, and now I look, A, E, D. If I put in D to A, that would complete a cycle. So A, D is rejected, because it would make a cycle. So not the 12 then, but the 13's okay. So that's BF at 13. and 1, 2, 3, 4, 5. I've got my 5 edges. As I look at the vertices, every vertex is connected into my set, so that looks correct. So I can stop and add up, and the total there is 45. And again, let's put the units on it. It's 45 miles. Okay, the last step is to draw the resulting minimum connector, and there is a blank provided, but as I want to keep using this page, what I'm going to do instead is I'm going to highlight the minimum connector. Just remind myself what the edges were: CE, CD, AE, CF, and FB. Okay, there's my minimum connector, and there's 1 mark for drawing it correctly. The other 4 marks were allocated as follows. First of all, finding a solution that has 5 edges, given there's 6 vertices, that's worth a mark. Rejecting AD correctly is worth another mark. And then having the list in the correct order, which for Kruskals, just check at the end, should always be increasing numerical size, because you always start with the smallest. Having that list in the right order is worth the 3rd mark, and of course 1 mark for stating correctly 45 miles for the length of the minimum connector. Well, before I go on then, let's just reflect again about that question 4, where the question is, under what circumstances would AD form part of your solution? Well, why did we reject AD? Well, that's because it was going to complete a cycle. And what was the cycle? It was going to be A, D, C, E, and then back to A would have completed a cycle. Well, the whole point about a cycle is you don't need 4 vertices for the minimum connector on 4 edges for the minimum connector on 4 vertices. You only need 3 edges. So if our cycle consisted of AD, DC, CE, and EA, one of those is going to have to go. Obviously at the moment it's AD, but if AD was short enough, shorter than 10, or at least equal to 10, then AD could be considered as part of the minimum connector. So AD would have to be less than or equal to 10. In fact, if AD equals 10, it's going to be okay, because it would form an alternative minimum connector. And don't forget to say, because this is what the question asks, how much should it be reduced by? And so it needs to be reduced from 12 to 10, so that's reduced by 2. And again, there's 1 mark for stating that correctly, and the reasoning isn't required, but I've written it down there. So everything is crystal clear. Good. Let's move on then to another question, and once again it's one of the 16 mark questions, so there's a lot to it, and we have a frighteningly large table, because this is going to be the tabular form of prims that we're going to do. So we're after a minimum connector, and the context here is it's going to be rail connections for a high-speed rail network between 11 cities. Well, of course, if you're finding a minimum connector, that means you want 10 edges. So we're going to use prims to find the minimum connector and its length, and then reflect on the solution and give an advantage and 2 disadvantages. Then, in part 3, we're going to use Dijkstra's algorithm, and thankfully they give us a printed version to work on, and that's to find the shortest route from P to NR. Then there's a little tweak here, because they then want the shortest distance from P to NR if you only use arcs that are in your minimum connector, and that crops up because it has a connection with part 2 of the question. I'm going to move on, but don't forget you can always rewind the recording or pause it to read the question at greater length if you need to. So, here we go then for prims on this very large table. And again, don't forget that because you're after a minimum connector, if there are 11 vertices, we're going to need 10 edges. I'm going to once again list them downwards, so there's absolutely no ambiguity about the order in which I choose them, although I will also indicate as I choose them the order of choice, because that's crucial to getting full marks. Another thing that's absolutely crucial is on this tabular version, you highlight a column, and we're told to start from P, so there's my first column, but as soon as you choose a column you must delete the corresponding row. And that's because if you're, as in this case, going to choose an edge out of P, you don't want later on to choose an edge that goes back into P, because that would form a cycle. And when you can't see what's going on because you're doing the solution in a table, this is the method that prevents a cycle being accidentally formed. Okay, you're allowed to choose any value from highlighted columns. I've only got one highlighted column at the moment, so the smallest number there is the 125, and that's my first choice. So, here we go then. That's P to BR, and it's 125. That means BR has come into my set of vertices, so in comes BR, and out goes the corresponding row, BR. Now I'm looking for the smallest value in either of these columns. The numbers available to me are 150, 240, 105, 120, 230, 90. There you go, that's my best choice from amongst those two columns, and that's BRBM. But don't forget, you don't have to choose from the latest column that's come into the set. You can choose from any highlighted column. Well, that's connected me to BM, so in comes BM and out goes the row BM. And again, choose from the columns here. Those seem like quite large numbers, and as I look down the BM column there's a 90. That's the smallest of the numbers available from the highlighted columns. That's BM, M, and it's 90. So that's introduced M, in comes M, out goes row M. And again choose, there's some small numbers in this M column. Let me just check. These are all in the hundreds. All those are in the hundreds, and in the M column I've got a 35. So there we go, that's my fourth choice, and it's MLV. 35. So that connected me to LV. In comes column LV, out goes row LV. I notice there's still quite a small number over here, this 90. I'll just check the columns and see if there's anything smaller, and you can follow my cursor and just see I'm checking all the other numbers. No, that 90 is my number 5 choice, and that's M to LD. Round about now, can I just remind you, you've got to be ruthlessly systematic. You don't want to find you've made a mistake part way through doing something where there's so many numbers to deal with. Okay, that connected me to LD. In comes LD, out goes LD, and now I'm looking through my columns to find the best number so far. 150, 240, or from this column 105. Anything beat 105? No, I'm just checking the remaining columns to see if anything is better than 105. No, that 105 is going to be my 6th choice, BR to S. 105. That connects me to S. In comes S, out goes row S. And again, choose from any of the columns. And in the S column there's a nice small number. That one is going to be my 7th choice, and that's S to LN, 80. Well, that connects me to ln. In comes ln, out goes row ln. And again, check down to see the best number you can find. Nothing left there. 150 there. 80 here. A quick glance confirms that's the best one. ln to f, 80. That brings in f. In comes f, out goes f. And now, notice I've crossed out most rows. There's only 2 rows left to look at. So I can choose from 115 or 230. 160, 175, no, not the 255. And then some numbers down here. Well, that 115 is the best remaining number. So that's ln to nr. 115. That's my 9th number. There is only one left to choose. Okay, ln to nr. That brings in nr and out goes row nr. There is actually only one row with any numbers left in it now. That's nc. And actually, I can choose any of those because they're all in highlighted columns. So it has to be the 175. That's my 10th number, 175. And that is LV to NC. Now just for completeness, I will finish off and say that brings in NC, in comes NC, out goes NC. And now there are no remaining numbers. Okay, well, let's add that up. And I did this previously, and it's 985 miles. Okay, just reflect on the marking of that for a moment then. Clearly there's 1 for the answer, and the other marks are given. 1 for correctly using a tabular method. 2 of the marks are for the correct choices. So your order of choices as you go down here has to be correct. So there's 2 marks for correct choices, and then in your tabular method 1 mark is for crossing out the rows and showing that you are actually understanding why in the tabular form of prims you have to delete the rows to prevent yourself accidentally forming cycles. Right, let's move on then, because our next job is to draw this minimum connector. And here's the blank they give us. I'm just going to go through the edges as we chose them just now. So we had P to BR, BM to BR, BM to M, LV to M, LD to M, S to BR, LN to S, F to LN, LN to NR, and NC to LV. Well, there we go. It certainly looks like a tree. I see there's no cycles, and there's 1 mark for that complete tree. Well, now then, let's reflect on the advantages and disadvantages of using a minimum connector for our rail network, assuming that all those purple lines represent the shortest distances between these various towns, which now are beginning to look to me suspiciously like Bristol and London and Plymouth and Southampton and Folkestone. Anyway, you can make up the rest for yourself. What advantages are there? Well, if you're going from BR to BM, and that's the shortest route, that's definitely an advantage. So you've used the shortest lengths of track. And in fact, you've covered the whole network using the shortest amount of track. However, in terms of disadvantages, one of those is because it's a tree, there's no redundant edges. In other words, if a line breaks down or a tree blocks that railway line, there's no other way of getting from a town to another town. So it's sort of, what shall I say, liable to break down. What about another disadvantage? Well, if you're going from P to BR, that's the most direct route. But if you're going from P to F, I'm not necessarily sure that this would be the most direct route. So just because you're using minimum connectors between these various towns doesn't necessarily mean it's the shortest route overall. Can't be too cast iron about this, but I think I would have to say some journeys will not be the shortest path. So between those particular vertices, and there's simply one mark for each advantage and disadvantage. Okay, well done concentrating so far, and here we go. There's a lot of focus required for the last step, where we're going to do Dijkstra's algorithm to find the shortest route from P to NR. So I'm starting at P. This is box number 1. It's 0 distance so far and no working values. Okay, there's a lot of lines and edges here, so I'll be as thorough and careful as I can, and I'll talk you through how I would make sure I don't make any omissions or mistakes. I'm starting at P, and you'll notice I'm ringing the vertices that I've used. So once a vertex is ringed or has a box completed by it, you never need to go back to that box with any further working values. So far then, at P the distance is 0. 0 plus 125 takes me to BR. 0 plus 240 is a direct route over here, 240 to LN. P at 0 plus 150 takes me here. And there's only 3 edges out from P, so I've done them all. Now, step back and look for the smallest working value, which is the 125. That becomes the permanent label here, and it's box number 2. Imagine you're at that point at this moment. Where can you get to from there? And your distance will be 125 plus the edge length. 125 plus 90 takes you to what I think is probably Birmingham, so that's 115. 125 plus 230 takes you over here, so that's 355. Where else can I go? 125 plus 120 is 245. Now I don't enter that value because there's a better value already in the box. And then 125 plus 105, well, that's 230, and I've already got a much better value in the box there. Okay, now step back, look at all the working values and pick the best one. That's the 115. I realised when I wrote in the 115 that that might not have been the best choice so far. Let me just check my calculation there. That should be 215. 125 plus 90 is 215. Right, so 150 is my best value. This is box number 3, 150. Okay, so I'm now at S. Where can I get to from S? Don't go to any of these points that have already been permanently labelled, but I can go to BM. 150 plus 135, well, that's going to be 285. No, I don't want to put that in because I've got a better value of 215 already in there. So 150 plus 80, that's 230. Yes, I will write that in over here. And then 150 plus 150, 300. Okay, once again, look at all the current working values. 215 is the best one. It becomes the permanent label, and this is now box number 4. Go everywhere you can from here with a starting value of 215. 215 plus 90 is 305. 215 plus 120 is 335. 215 plus 160 is 375. Well, I don't write that in because it's not better. And keep checking, there's another one here, 215 plus 120, that's 335. No, I don't want that either, but I did need to check it. Then the other two connections are already boxed. Okay, reflect again on all the working values, and here is, I think, a little possibility for error built in. So it's the 240 over here at London, and then notice there's a 300 down here and 305 up at M. Keep an eye on those. Okay, LN is the next one. 240, 230 is the best value. 230, and it's box number 5. Where can I get to from there? 230 plus 80 is 310. No, I don't think I ought to be writing in 310, because 300 is better than that. Where else can I go? 230, not to this vertex, or the boxed ones. 230 plus 115, that's 345. That is better. So in goes the 345 here. That's all the vertices I can go to from LN. Again, look at all the vertices, and this one bottom right, I think it would be very easy to overlook. But this one down here is going to be my next vertex. So that's vertex 6, and its length is 300. Actually, the two vertices I can reach from there are already permanently labelled. So that's it for F. Now it must be the 305 up here. Box number 7, total length 305. Okay, where can I get to from M? By the way, I will just, for completeness sake, ring F. 305 plus 35 is 340 at LV. 305 plus 90 is, well, I think it's going to be more than the 335 that's already there, isn't it? That's going to be 395, and this is 335, so I don't need to do that one. And this is already permanently boxed. Okay, I'm running out of vertices, and casting my eye over those, 340, 335, 345. So LD is my next vertex, and 335 is the permanent label. Okay, 335 plus 100 is 435. Nope, I don't need to write that one in at LV. 335 plus 210, that's a new box. I will have to write this in. It's 545. And from here to NR, 335 plus 175, 510. No, that's too big. There's already a better value in there. Okay, only 3 vertices left to go, and I've got 340, 545 and 345. So my 9th box is LV, and the distance is 340. 340 plus 175, that's 400, 515. Oh, that is better. In goes 515. And from LV I can't get anywhere else that isn't already boxed. My next best value is at NR, and it's 345. By the way, that's going to be my solution in just a moment. This is the point I'm supposed to stop, but sometimes they ask you questions about an extra road or a road being closed, so I will complete the solution, which I normally would do anyway. So from here, 345 plus 255, that's about 600. It's too much. So the existing value of 515 is the best one and becomes my permanent final box to label. I will just say there is no mark for doing the final labelling on this box. Okay, so let's reflect on the solution then. I want the shortest route from P to NR, and working backwards, 345 take 115 is 230, and 230 take 80 is 150, 150 take 150 is 0. Well, there we go then. So the shortest route is that one in the correct order. It's P to S to ln to nr. Let's consider how this is marked for a moment. There's one mark for a substantially correct method, showing that you're doing Dijkstra's method and getting at least part of it right. There's a mark for getting the working values correct, and I can't emphasize this enough. Putting all the ones you need, not putting in redundant extra higher working values, and putting those two values in, because both of those would have been entered before finally boxing number 10, if indeed you did stop at box number 10, because we were asked to find the shortest route to NR. There's no penalty for carrying on and completing box number 11, by the way. And as before, there's one for getting the labels correct, in other words, the actual right-hand numbers, the distances, and again there's one mark for the order being correct. As always, there's one for the route and one for its length. We know the length, it's there in box NR, but we ought to state it, so 345, and these were once again miles. Now we just have that last tweak at the end of the question to consider, which is what would your shortest distance from P to NR be if you were only using the minimum connector? Well, I don't know if you remember which routes we had in our minimum connector, but PS wasn't amongst them. In fact, the minimum connector routes included P to BR and BR to S, but not PS. However, S to LN was in there, so was LN to R. So my route from P to NR, if I only use the minimum connector, has to be P to BR to S to LN to NR. So in total that gives me 125 for that section plus 105 for that section, which of course is longer than the 150 directly from P to S, although the other two sections remain unchanged. And that gives me a total of 425 miles, which not surprisingly is greater than the 345 miles if we could do it directly and weren't limited to only the minimum connector routes. And of course this is linked to that disadvantage earlier, that some journeys, including this one from P to NR, would be longer if you could only use the minimum connector rail network as opposed to any of the routes. And with that second long question, I've come to the end of this presentation. So all the very best with the rest of your revision.